Mr. Taru, in this video we're going to be introduced to simplifying expressions that have rational or fractional exponents. We're going to look at the definition, break down some basics, and then do 6 examples. In the description you'll find timestamps to jump ahead to any of these 6 examples. I kind of go from easy to hard. You'll also find lessons that I've already done related to this concept and more advanced lessons so you can kind of see where it's going to go in your math studies if you are interested. Let's get started. So, the definition of a raised to the m over n power. What does it say? It says if the nth root of a represents a real number, so we're not talking about imaginary or complex numbers here, and m over n is a positive rational number. Let's not forget that we are talking about rational numbers, fractions, which the numerator and denominator are integers, basically like 1 over 2. 1.1 over 2 is not a properly formatted rational expression or number. And we have n is greater than or equal to 2, then some base of a, which may be a number, it may be a variable, it may be a full expression with a combination of numbers and variables together, raised to the m over n power, can be written 2 ways. It can either be written as the nth root of a raised to the power of m, or we have this nth root of a to the m power. Now, for years I kind of defaulted right to this notation, but really honestly now I'm starting to prefer this way of rewriting a to the m over n power because it's going to keep you reminded that to simplify you should make numbers smaller before you make them bigger. So it reminds that to me it kind of reminds that you should be taking the nth root of a first, bring the numerical values down, and then raise it to some power of n. Keeping those numbers smaller will make it easier for you to do these problems without the aid of your calculator. Now, what does this mean here? Why are they including that the nth root of a represents a real number? You can take, say, the third root of negative 8 and say that that is equal to negative 2 because negative 2 raised to the third power, be careful to keep this negative inside a set of parentheses, raised to that power of 3, is negative 2 times negative 2 times negative 2, which is, negative 8. So negative 2 cubed equals negative 8, thus that is why the cube root of negative 8 is equal to negative 2. You can take an odd root of a negative number and get a negative answer. That is a real value. Negative 2 is a real value. However, you cannot take an even root, say the square root of a negative number, say like negative 9. What's the square root of negative 9? Is it 3? 3 times 3 is positive 9, not negative 9. Well, maybe you say that the square root of negative 9 is negative 3. Well, if you do it mentally, which hopefully we can do that, but if you check it with a negative 3 wrapped in parentheses raised to a power of 2, negative 3 times negative 3 is, again, positive 9, but we're looking for the square root, or an even root actually. That's what's more important, the fact that 2 is even, of negative 9, and there just isn't a real solution. Negative 3 squared is equal to negative 3 times negative 3, which is, again, that positive 9. No, actually, it's beyond the scope of this lesson, but the square root of negative 9 is actually equal to something called 3i. It's an imaginary number. So, that needs to keep you thinking about the domain of these expressions. Your book may be saying that for these type of problems where you're simplifying expressions with fractional exponents to assume, or they're telling you that the base, if it happens to be a variable, is greater than or equal to 0. So I'm kind of adding some complexity here, which is really necessary, but some books, when they first introduce this concept, avoid this complexity by saying the base is always going to be positive. But if they don't do that, when you are being told that you have to work with only real values and you're taking an even root of some expression, if that is an unknown value, like say a, then we need to understand that a has to be greater than or equal to 0. But as you saw with the cube root of negative 8, an odd root of a value, you can take the odd root of a positive or negative value, or 0, but that's not very interesting. Therefore, we know that, or we can take from that, that a is some value between negative infinity and positive infinity. Or, your book may state, as mine does for my kids, who are hopefully going to be using this as a resource, that a is an element of all real numbers. It's sort of funny looking, almost like an E notation. It's a form of set notation, is a set of all real numbers. In other words, you can take on square roots of 7s and negative values, positive values, fractions, whole numbers, integers, whatever. Now, we need to remember, as we work through these problems, that the square root of a squared, and really this is technically true for like a 4th root and a to the 4th, or 6th root and a to the 6th. Anytime these, you have an even power and an even index, which are the same number, that it's acting as an absolute value symbol. What am I talking about? Negative 3 squared, negative 3 times negative 3 is 9. The square root of 9 is positive 3. So I took negative 3, I applied a power of 2. From that answer, applied a square root and got a positive 3. Same number, but the negative went away. So the square root of something squared is actually acting as the absolute value of that value, and we get, in this case, our example is 3. So square root, power of 2, acts as an absolute value function. That's important when you're considering the domain of the expression inside your radical. And remember, when we're given a radical notation in our textbook, we're looking for the primary root, the positive root. Now, that's a correct statement if the index is even. You can take an odd root of a negative number and get a negative answer, but we're looking for that primary root. And so this all will come into play as we do our examples later. Anything to the 0 power is equal to 1. If your teacher has always said this is true just because the textbook says so and has never validated it, we can show that this is true by using our properties of exponents and say something like, well, you know, anything divided by itself, like a to the n divided by a to the n, or 5 divided by 5. Anything divided by itself is equal to 1, right? So we know this is equal to 1. But we also know that when we divide like bases, we subtract the exponents. Well, that's a to the n minus n, which is a to the 0, which, when we see it this way, knowing that we're dividing something by itself that's equal to 1, then it's easy to understand that, yes, any base raised to a 0 power is equal to 1. And why is it that I'm including this property of, we're trying to remind you that a to the negative n power is equal to 1 over a to the n. Didn't we just say that our fractional exponent had to be positive? Well, that's in the definition of a to the m over n, but that's just to kind of clarify and make a precise definition. When we have a power which is negative applied to our base, then we can just move that base to the denominator if the original base was in the numerator, or you can do the same thing here. If we have a base with a negative exponent in the denominator of a fraction, we can move that base, just the base, with the negative exponent up to the numerator, and it'll make the sign of that exponent change. Now again, we don't have to say it's that way because I said so. You can do like a little example here and say that, well, a to the n power over a to the 2n power, which, by the way, is the same as a to the n. We're going to do a little review of properties of exponents. When are you allowed to multiply exponents like this exponent of 2 times the exponent of n? Well, that's a to the n squared. When you have like a power to a power, that's your multiplication property of exponents. And now we're looking at a to the n over a to the n squared, which just means we have two of those bases, a to the n times a to the n, and anything divided by itself is equal to 1. So we're looking at 1 over a to the n. Now, why am I bringing this up as an example to help us justify that a to the negative n power is equal to 1 over a to the n? Well, I'm showing with properties of exponents how a to the n over a to the 2n is equal to 1 over a to the n, but if I use a different property of exponents and remind you that when we divide like bases, you subtract the exponents, a to the n over a to the 2n is a to the n minus 2n power, which is equal to a to negative n. So I just worked the same problem out twice. One way, sort of using one property of exponents, coming up with a to the negative n power, and showing the work another way, getting 1 over a to the n. So this isn't really a proof exactly, but I'm trying to help you understand why that exponent is changing sign when you move the base from either the top of the fraction down to the bottom or vice versa. Let's get on to our first example right now. So here we have example 1, and we have 16 raised to the 5/4 power. Now that is that entire base. It is well, it is only 16. It's not there's no negative there, but it is the entire base being raised to that 5/4 power. And I'm going to write this in sort of both forms that we saw in that definition of a to the m over n power. Now one way is to write this as, well, the 4th root of 16 to the 5th power. Again, recognizing that that numerator is the power that's going to be applied to the base, and the denominator of a rational exponent is the index that we are applying to a radical. If you write it like this, you might be tempted to work out 16 to the 5th power. Well, if we're doing a test or working with our homework and we're not allowed to use our calculator, I definitely do not want to do 16 times 16 times 16 times 16 times 16. That's going to be a huge number, and then I'm going to have to come up with some number times itself 4 times that equals that very large number. That is not the best way of approaching this problem. No, what you really want to do usually with these problems is to make numbers smaller before you make them larger. Simplify before you kind of make more complicated. And you can do that in either one of the ways that I write this, but a better way to write this is that it is equal to the 4th root of 16 raised to the 5th. Now, they mean exactly the same thing, but when you write this, it may, your expression this way, hopefully it's going to remind you that you should be doing the root first. So 2 times 2 is 4, times 2 is 8, times 2 is 16. 2 to the 4th power is equal to 16, thus the 4th root of 16 is equal to 2. And keep, keep that parentheses around there. It's important, especially if you have something like a negative being involved somewhere. So 2 to the 5th power, that's certainly something much more manageable. 2 to the 5th power, 2 times 2 is 4, times 2 is 8, times 2 is 16, that's right where we came from, times another 2, 2 to the 5th, is equal to 32. Simpler. Now, this is not the only way that you can look at this problem and come up with this final answer of 32. No, when you're working with expressions that deal with radicals and fractional exponents, you normally have a wide range of how you want to find your way to the final answer. Like, instead of using radical notation, maybe I want to work with properties of exponents. Maybe I want to rewrite the 16 as 16 times some other form of 16 and work with coming up with two fractions, or the two fractions that add to 5 over 4. Remember, when you multiply like bases, you add the exponents. And you need common denominators when you add fractions. Well, look at this. We can write 16 to the 4 over 4 power, and then this 16 to the 1 over 4th power, right? When you multiply like bases, that's equal to 16 to the 4 over 4 plus 1 over 4, which, of course, with that common denominator, 1 plus 4 is equal to 5. Now, 4 divided by 4 is equal to 1, so now we're looking at 16 times, well, 16 to the 1/4 power, which is fine if you know that we need to take the 4th root of 16, but since we're just getting introduced to this, maybe you write this as 16 times the 4th root of 16. And the 4th root of 16, as you just saw us come up with, is equal to 2, and 16 times 2 is also equal to 32, which is, well, the answer that we already know, this equals. So there, I'm giving you a couple of different ways of looking at the same question. You have that flexibility. Use the process or the notation that works best for you to get that correct answer. We have 125 raised to the negative 2/3 power. Well, that's the cube root of 125 then raised to the negative 2 power, and the cube root of 125 is equal to what? 5 times 5 is 25, and 25 times 5 is 125. Yes, the cube root of 125 is equal to 5. Now that's being raised to the negative 2 power, and we just, on that first page of notes, we talked about how if you have a base raised to a negative power, then you can just simply move that base either from the numerator down to the denominator or vice versa, from the denominator of your fraction up to the top. So this 5 over 1, or this 5 raised to the negative 2 power over 1, can be written as 1 over 5 squared, which is equal to 1 over 25. Now, just to kind of give a little bit of bonus content, we are taking a cube root here, so we can take the cube root of a negative number. As we talked about, the cube root of negative 8 was negative 2. We could be taking the same problem but have a base of negative 125, and that becomes the cube root of negative 125 raised to the negative 2 power, and the cube root of negative 125, negative 5 times negative 5 is positive 25, and positive 25 times negative 5 is negative 125. So the cube root of negative 125 is equal to negative 5. And still, that base with the negative exponent can be moved down into the denominator of our fraction to make that exponent positive, only now it's a negative 5. And negative 5 squared, well, negative 5 times negative 5 is equal to 25. So actually, in this particular case, we could change the problem, introduce a negative sign on our base, and still come up with an answer of 1 over 25. That's not always going to happen. Basically, our negative is, going away and giving us a positive answer because we have that even power. And a negative number raised to an even power is always positive. Here we have the 4th root of 7 squared. Can we rewrite this expression so it has a, maybe a smaller power, a smaller index, or both? And working with radicals actually is usually not very friendly. When we have maybe more than just a square root and some powers inside the expression of that radical, it's actually usually easier to work with it as a fractional exponent. That's why we're talking about this lesson of introducing simplifying expressions with rational exponents. This is going to be 7 raised to the power of 2, and has the fractional or rational exponent will have a base which is equal to the index of the radical or the root of 4. Well, we can divide both the numerator and denominator by 2, reduce the fraction. And we have 7 to the 1/2 power, and now the problem was to simplify this expression. That's just the 7 to the 1 power second root, or the square root of 7. Now let's get on to our last two examples that involve some variables inside the radical. And example 4, we have the cube root of 125 times x to the 10th power. Now we're starting to deal with variables inside of our radical, and we need to make sure that we pay attention to the domain here. We're taking the 3rd root of a number being raised to an even power. And whether this is an even power or not, on our exponent, or our variable of x, we're taking an odd root, so x can take on the domain, or has the domain, this expression has the domain, where x can be a member of, well, it is going from negative infinity to positive infinity, or that x is an element of all real numbers. It's not restricted to just being positive or 0. So I like working with this problem in that fractional exponent, or that rational exponent notation. So I'm going to write this as the 125 raised to the 1/3 power. If you prefer, you can write the cube root of 125. That's perfectly okay. And then we're going to multiply that by, actually we can use that property. Let's do this. Let's use the property of multiplication with, well, we were introduced to it as a property of square roots, but it's really a property of radicals. And write this as the cube root of 125 times the cube root of x to the 10th power. Now, we should already know the cube root of 125, well, we just did in the previous example, is equal to 5, and just, pop that right out. Cube root of 125 is equal to 5. 5 times 5 times 5 is 125. But here with the variable as our base, maybe it can be a little bit more complex here. So we're going to write this as 5 times x to the 10 over 3rd power. And I'm going to use more of the properties of exponents to simplify this, like I showed you in the second version that I did in blue on example number 1. I'm going to write this as 5 raised times x to the, now I'm looking for multiples of 3, so it divides out evenly, 3, 6, 9. So x to the 9 over 3 times x to the 1 over 3. When you multiply like bases, you add the exponents, and 9 over 3 plus 1 over 3 is 10 over 3. Well, that's going to give us 5x, and then 9 divided by 3 is equal to 3. So we're looking at 5x cubed. And now there's really nothing left here with our x to the 1/3, except to remember that this is x raised to the power of 1. And then from that, the 3rd root is taken, which I'm saying, I'm putting 2 fingers up, but it's the 3rd root. So this is going to be 5x cubed times the cube root of just x. We don't need to worry about absolute value symbols maybe possibly showing up in our final answer here, like we will in our next example, because we have an odd root, and there's never more than one possible answer when you take an odd root of some number or some expression. But over here, we will have this issue. Now, we have an even root, a 4th root, being applied to 81 times x to the 12th power times y to the 8th. Now, with an even root, you cannot take an even root of a negative number, which, is that a problem? Well, we have x being raised to an even power, and we know that any number, whether it's positive or negative, when it's raised to an even power, it comes out to be positive. Y is also being raised to an even power. So here with this expression, we have that x is an element of all real numbers, which means that it can take on positive numbers, negative numbers, or 0. Can be a decimal, can be whatever. Positive, negative, 0. Same thing with the y being raised to an even power. Because both of these are being raised to an even power, we don't need to worry about taking an even root of that value. So x is an element of all real numbers, and y is also an element of all real numbers. Don't forget, that means from negative infinity to positive infinity. Okay, great. Well, let's separate this like we did in this previous question. We have the 4th root of 81 times the 4th root of x to the 12th power times the 4th root of y to the 8th. Well, that is going to be the 4th root of 81. Again, we're doing this without a calculator, so it can't be too complicated. 2 times 2 is 4, times 2 is 8, times 2 is 16, too small. 3 times 3 is 9, 9 times 3 is 27, and 27 times 3 is 81. 3 to the 4th power is 81. So the 4th power, or the 4th root, excuse me, of 81 is equal to 3. I'm going to write these variable bases with a rational exponent. So we're looking at x to the 12 over 4th power, and we're looking at y to the 8 over 4 power. Well, both of these divide out evenly. That's nice. We didn't have that situation when we had a power of 10 and an index of 3. So this is just going to be x cubed. And this is going to be y, and then 8 divided by 4 is 2, so y squared. Depending on the directions of your textbook, it may give you this as saying, okay, this is good, this is the final answer. But if y is an element of all real numbers, and you take any number, whether it's positive, negative, or 0, and square it. A negative number squared is positive, and a positive number squared is positive. Well, that's fine, because look at our notation here. It is the fourth root of 81x squared y to the 8th power. And we are looking for a principal root, a positive root. We're not looking for like a plus minus here. I'm not asking for specifically a negative value from this. I'm looking for a fourth root. I need to have an answer which is positive. So is it okay to have an x cubed? Is it okay that with x initially having an even power, which means that this is always going to be positive, which means we can always take an even root. We're talking about radicals that give real values as answers. If x is a negative number, then a negative number cubed, like again, negative 2 cubed is negative 8, that would make this expression negative, but we're not allowed with this notation and how our book is asking for principal roots when we're given these radical signs. We need to keep an absolute value symbol around this x cubed to make sure that this expression is giving us that positive fourth root that the problem is asking for, and this is our final answer to example number 5. I got one more example coming up right now. Example number 6. And I'm leaving example number 5 up here for a reason, and I'm even going to color code it and kind of like, this is different. These look really, really similar. It's just a root of a monomial. A root of a monomial, one term. So why are they different? Well, that definition, right? The nth root of a has to represent a real number. Now, if we take a value, the variables just represent unknown values. So if x happens to take on a negative number, and we raise that to the 5th power, a negative number raised to an odd power comes out to be a negative answer, but yet we're being asked to take an even root. So it doesn't need to say it in the directions, but we need to understand that we need to think about these radicals before we just spit out an answer, unless of course your book says assume all values and assume like x and maybe y are all greater than or equal to 0, then I'm kind of giving you more advanced lesson than you really need. But if a value is raised to an odd power, and then we're taking an even root, 2, 4, 6th root, whatever, of that expression, then we need to understand that this implies that x is greater than or equal to 0. And actually, being equal to 0 is not very interesting because any root of 0 is 0, but whatever. Now, we're going to say that we have the square root of 32, so we're going to write this as a factor. What's the largest factor of 32, which is a perfect square? It's not 4. 4 times 8 is 32, but within 8 we have another factor of 4, so it's actually 16. So we're looking at the square root of 16 times the square root of 2, using that multiplication property of radicals. 16 times 2 with the same index is equal to 32. And we're going to write this as times x to the 5th power, then divided by our x to the 5 over 2nd power. Power over root. Power and the index of our root once again. Square root of 16 is 4. Square root of 2. Like the previous example, we're going to write this with this base of x with a exponent that comes out to be, evenly divided. That's going to be x to the 4 over 2, and then we're going to multiply that by x to the 1 over 2. Again, I'm trying to split this base up so that we have an exponent that's basically a whole number. If it's negative, we'll just move that base down to the denominator in a moment. But 4 over 2 plus 1 over 2 is equal to 5 over 2. So this is an equivalent expression to x to the 4 over 2 times x to the 1/2 is equivalent to x to the 5 over 2nd power. Now we're going to be looking at, 4 divided by 2 is 2. So we're looking at 4x squared and power root. So x to the 1/2 is the same as the square root of x. So we're looking at the square root of 2 times the square root of x, which is the square root of 2x. And this is, is this fine? can I leave my final answer in this format, or like in the previous example, do we need to introduce a set of absolute value symbols around our variable that's in our final answer that's not still in the radical? Do we need to write this as 4 times the absolute value of x squared to make sure that this expression remains positive like we're looking for, the principal root of the square root of 32x to the 5th? Well, first of all, because this variable of x is raised to an odd power, and then, with that even root implies that x from the original problem has to be greater than or equal to 0, that alone would basically mean that we don't need to keep these absolute value symbols. Like if it was x cubed, we'd still be okay, because a positive number cubed is still going to be, well, positive. But we have that base of x being raised to an even power, so by default, any number raised to an even power is going to be positive, and therefore this is fine as a final form of our last example. I miss it true? Bam! Go do your homework.